Hello, my name is Jeremy.
And I'm Amanda.
And today we're going to be going over a lecture on tautomerization.
In organic chemistry, tautomers are two molecules with the same molecular formula, but different connectivity. Constitutional isomers, in other words, which can interconvert in a rapid equilibrium. The most common tautomeric relationship in organic chemistry is the Keto-Enol pair. Tautomerization is the process of isomerization of one tautomer into another tautomer.
Keto-Enol tautomerization. When we draw a ketone or aldehyde using a Lewis structure convention, we show a double bond between the carbon and the oxygen. This is known as the keto form. It turns out that the ketones and the aldehydes form often exist in rapid equilibrium with a tautomeric form known as enol. So we have our keto and our enol forms. The alpha proton of carbonyls, as you recall, are somewhat acidic. The pKa of acetone, for example, is approximately 19. In the formation of enol, a base abstracts an A proton from a carbonyl compound, and that same proton, or a proton on a nearby acid group, is transferred to the carbonyl oxygen. The result is a new functional group that combines both alkanes and alcohol characteristics. Hence the term enol. The deprotonated form of an enol is an enolate. Tautomerization is a process in which a tautomer is converted into another. The process is either acid or base catalyzed. The mechanism of the transformation involves two steps: protonation and deprotonation. The order depends on whether the mechanism is acidic or basic. For acid catalyzed, it's protonation and then deprotonation. And for a basic catalyzed tautomerization, it goes from deprotonation and then protonation occurs.
Let's look at an example of acid-catalyzed tautomerization, where protonation precedes deprotonation. We begin with an acetone, and in the first step, a lone pair from the oxygen attacks a proton on the hydronium ion, leaving us with water and a resonance-stabilized cation. In the second step, where deprotonation occurs, water acts as a base to deprotonate the cation. And this creates 1-propene-2-ol, and it also regenerates the catalyst, which was the hydronium ion.
Next, we have base catalyzed tautomerization. In step 1, we have deprotonation, which precedes protonation. The first step involves the use of a hydroxide ion to deprotonate the acetone, thus forming water, as well as the resonance-stabilized enolate anion. For the second step, water acts as an acid to protonate the enolate anion, and results in the creation of a 1-propene-2-ol and regenerates the catalyst hydroxide ion.
Let's look at equilibrium. For simple carbonyl compounds, equilibrium favors the keto tautomer. This equilibrium distribution can be explained by bond strengths. The enthalpy of dissociation of a carbon-oxygen double bond is much greater than a carbon-carbon double bond. Thus, the stronger bond in the keto tautomer stabilizes the compound, making it more favorable at equilibrium. As a general rule, the keto form of carbonyl is lower in energy, and thus predominates at equilibrium. Acetone, for example, is present at 99% keto form at equilibrium, whereas the enol tautomer is only present at approximately 1%.